Hello. Hello, guys. You're welcome back to Yad Academy, and this is a part B of our exams prep tutorials. So, in this problem, it says a balanced three-phase system has a load consisting of a balanced star in parallel with a balanced delta. The impedance per phase for the star is 8 plus 6 j ohms, and delta is 24 plus 18 j ohms. The impressed voltage is 240 root 3 volts line to line. A, which is calculate the line current, and B, calculate the current in the delta connected load. If this is the first time you have been on this channel, please do well to subscribe to support and make sure you share if you found it very useful. How do we approach this problem? So this is simply AC plus three-phase system. So for a three-phase circuit, it's just an application of AC, right? That is alternating circuit. But this time around, you want to step it up to three-phase, not just a single phase. Now, it's a balanced three-phase system, right? It has a load. Now we are having two parallel loops, but one is a star and one is a delta. Let's analyze this problem very well. If you meet it anywhere, you shouldn't get this wrong. So a balanced star, then you have a balanced delta, right? These are the two things you should take note of. A balanced star and a balanced delta. The impedance per phase for the delta and for the star is 8 plus 6 ohm, and the delta is 24 plus 18 j ohm. And the impressed voltage is 240 root 3 volts line to line. Before you solve this problem, please, the first thing to do is to model this problem and you write it as a circuit before you understand and the impedance for the delta. Now, after doing this, you realize that the voltage across this now after doing this you realize that the voltage across this, that is our VL, the line voltage, right? This is the voltage across this. Once you model this at this point, you are almost there, but there's one thing you're supposed to do. You are supposed to make sure that the two configurations are the same before you can find the total impedance. Whenever you want to combine the total, please make sure they're of the same configuration. And it's always advisable to convert it to star. Star actually is somehow like the default configuration when it comes to three phase. Even if the problem doesn't say that it's a star or delta, please treat it as a star. Is one thing you're supposed to know. Now, for a balanced star in parallel with balanced delta, we are going to convert the balanced delta to a balanced star. The word balance means all the three phases have equal impedance, right? Because of that, we are going to have the 24. So the 24 plus 18 j ohm, which is in the delta. Remember from what do we say? When you're doing delta star conversion, whenever you want to convert it from delta to star, and they are of equal value, what do? You simply divide it by 3. So note this down. Star is equal to delta over 3, or delta is equal to star times 3, provided the same impedances are found on each phase. So I'll just divide this by 3, and I'm going to get 24 divided by 3 is 8, plus 18 divided by 3 is 6j. Therefore, my this impedance across the star is 8 plus 6j. Impedance across the delta becomes 8 plus 6j. Now they're of the same configuration, though I've made here delta, but it's actually star. Okay. Once I've made them of the same configuration, then I can find my total impedance. The first question is saying we should calculate the line current. To calculate the line current, you know that when you are doing our normal electrical circuit problems, you always have to find the total impedance here divided by the total voltage to get a line current. Is that not it? Therefore, let's find the total impedance here, right? So to find the total impedance here is simply the parallel combination. And also remember that we are dealing with the complex domain. So the parallel combination of 8 plus 6j, 8 plus 6j, right? And this becomes 8 plus 6j times 8 plus 6j over 8 plus 6j, or plus 8 plus 6j. It's similar to what you have been doing. And remember, if you have any two resistances in parallel and they are equal, their parallel resistance is half of them. So obviously we get 4 plus 3G. Now this is the total impedance. We need to find the line current. To find the line current, we need to get this in the normal magnitude and direction form. Okay, so let's find the magnitude. So square root of 4 squared plus 3 squared obviously equals what? 5, right? Now we know that our impedance is 5 ohms. We come back to our voltage. What is the total voltage? From the problem, we're given that the impressed voltage is 240 volts line to line. That is what I indicated here, that between this line and between this line, I have 240 volts. Okay. Now, for me to simplify this, remember that from the beginning, we converted this to what? The star configuration. And remember, in star configuration, your line voltage and your phase voltage are never the same. That is one thing you should take note of. Your line voltage and your phase voltages are not the same. What's the relationship? To find our phase voltage, because now we have per phase. Remember, let's see something here. The impedances I'm using here is per phase. This is the impedance per phase for star is this. The impedance per phase for the delta is this, right? So the impedance per phase is what we are using now. Therefore, since we have our line voltage given, I need to find the phase voltage in order to get the accurate line current. Let's see something. So here I'll have my voltage given as 240 over root 3. To find my VP, is become 240 root 3 over what? Root 3. Is that not it? Therefore, my answer is 240 volts. So my final line current IL is given as what? We have V over what? My Z. Therefore, I have 240 over 5. And what's the answer? So 240 over 5 is given as 48. So we have 48 amps. 48 amps. So here I use just a single impedance. You could have also used three, all the three, right? And you find the opposite way, or you do it the other way around. So this is how we do. Now we find our line current coming in as 48 amps. What's the next question saying? He said calculate the current in the delta connected load. What is the delta connected load here? So here, for us to find the current in only the delta, meaning that we need to find the voltage across the delta phase alone. Then you also find the impedance and you can get a current. But let's take note of something. The question gave 240 root 3 line to line. And remember, in a delta connection, the phase voltage and the line voltages are the same. In this simple model that you've done here, if you have the voltage across a parallel connection, the voltage across the ZS is the same as the voltage across the ZD. Like it's the same because it's parallel. Therefore, my voltage 240 root 3 now will be taken directly because I want the delta. Please don't confuse yourself. When you wanted to find a current, you have to convert everything to star. That is what we did. Now the question is asking us to find a current only in the delta. So we are moving to the delta configuration. We are no more using this 8 plus CJ in a way. We are going back to the delta configuration. Okay. So we have our voltage across VP across the delta, right? Is simply equal to the VL across the line to line, which is equal to 240 we maintain. Once you have this done, what is the impedance per phase for our delta? The answer was what? 24 plus 18J, right? So therefore, to find my current in my delta is simply equal to my voltage, which is 240 root 3 over 24 plus 18J, right? So to do this, what do? You simply have to convert your 24 plus 18 magnitude. So 24 squared, you have 24 squared plus 18 squared. What's the answer? 24 squared plus 18 squared. That will give us 30, right? 30. Therefore, my answer is going to be 240 root 3 over 30. What's the answer? You cancel, we get 8 root 3. What's the answer for 8 root 3? That is 13.856. 13.856 amperes. And that is how we solve a simple three-phase balance system, which is having two different loads in parallel. Please, at this point, if you have still not subscribed, do well to subscribe to support and invite your friends on board to also have value in this. Let's go to our next problem. Okay, so this problem said find the effective resistance of the circuit below, and we interestingly have all the resistances measuring 1 ohms. Okay, so we have to solve this problem. How do we simplify this problem? Please, whenever you want to simplify a complex um, connection, always think about series first and take two resistors at a time away from the terminals up here. Away from the terminals, you can see these are the what? The farthest part. You can clearly see there is no node here. These two resistors will be in series. Therefore, this and this will add to give us what? 1 plus 1. Now, this here as well, you have 1 plus 1 here, right? Let's do that first simplification. I have this to come down. This will move to this level. And this, sorry. Yeah. So at this point, remember that I've already combined this into so becomes 1. I'll have 2 ohm. I have 1 ohm. I have 1 ohm. Then I have my base here, which is 1 ohm. This also comes here, 1 ohm, right? This comes here. So now check something. I have 1 ohm here, then this become 2, right? So I have this 2 ohm, this here. Then I have 1 here. Then I have 1 here, right? So there's 1 ohm. Sorry, this is gone. Should go. Good. So this is 1. Now, after doing the first series simplification, the next thing to think about is parallel. Is there any series again? There's no series. At the farthest part, this and this are not in parallel because this is here, this is a delta. But I can see that this and this here, 2 and 1 can be simplified. So that is my next move. When I simplify, I get 2 times 1. I get 2 plus 1, which is 2 over 3. Therefore, I'll simply have this here, have this here, have this here, right? And I'll have this here. Then this and this will combine to give that. Okay, so here is 2 over 3 now. Here is 1, here is 2, here is 1, here is 1, here is 1. Take note of that. At this point, we have a delta configuration here, a delta configuration. For us to simplify a delta configuration, between any two resistors, you introduce one resistor. So I'll have one here, this and this, I'll have another, then I'll have another, right? Therefore, I'll have here to be A, here to be B, here to be C. Now let's find the values. So the value for my A is simply going to be equal to 2 times 1 over what? 2 plus 1 plus 1. That is 2 over 4, which is what? Half. The value for B is simply going to be what? 1 times 2 over 4. That is also half. The value for C is going to be what? Between 1 times 1, which is 1 over 4. Then after here, you redraw. Check the redraw. You move to this, which is this. Then right after here, you move straight to right from here, you move straight to this, right? Then this, right? 9C, okay? And this comes here, this comes down here, and this goes in. Good, right? Now this is my A. My A is 1 out of 2. My B is what? 1 out of 2. My C is what? 1 out of 4, right? This is 1. This is 1. Remember here is what? 2 out of 3, and here is what? 1. At this point, do we have any series? Yes. My 1 and 1 out of 2 here is in series. My 2 out of 3 here and my half is also in series, right? Let me show you clearly. This and this are in series. This and this are in series, right? Then I can solve. So I redraw, then I'll have this again. So I'll have 1 plus this, give me 1.5, right? So it becomes 1. Okay, that is 1.5. This node, I'll break it down here. Then this should give me, for this side, I'll have, check another series 2 connection here. 1 over 4 and 1. So this becomes 1.25 here. Or we say that 3 over 4, right? No, 3 over 4 is not 1.25. So that's going to be 5 over 4, right? So let's make it 1.25. That's what I remember. So, but please, it's not advisable to be living in decimals for this. Then this side will branch to this side, right? And I'll have 1 out of 2 plus 2 over 3. That's 7 over 6, right? So have 7 over 6, boom, right? Nice. Then everything here will go together to the 1 here, 1 ohm. So therefore, we have this today. So this and this are clearly in parallel, right? Simply get 1.25 times 7 out of 6, 1.25 plus 7 out of 6. What do we get? So that's 0.6034, right? Then at this point, you can see where we have ended. So I have my 1.5 ohm going into my 0.6034 ohm, 1.5 ohm. Then it will branch to this wire, which is 1 ohm. Therefore, my answer is 1.5 plus 0.6034 plus 1, right? What are you getting? So plus 1 plus 1.5. That gives an answer 3.103, 3.103 ohm. And that is the effective resistance of this electrical network. At this point, if you still haven't subscribed, please do well to subscribe and share to your friends. So we move to our next problem. Yes. So in this problem, it says the following single phase loads are connected to 415 volts three phase supply. Our ZR, that is on the red line, is 10 minus 15J. Our ZY, the yellow line, is 15 plus 10J ohm. Then our ZB, the blue line, is 8 plus 5J ohm. What is the current in the yellow phase? What is the current in the yellow phase? And find the magnitude of the current in the neutral conductor. So to find the current in the yellow phase, IY is simply equal to the voltage over what? The impedance dy. As simple as that. And this should be the voltage across Y, which is the same as the phase voltage VP. Okay. Now, they didn't mention anything, but remember, if nothing is mentioned, it is star. So it is star by default. Okay, by default. Take note of this. Therefore, my VP is simply equal to 415 over what? Square root of 3. Remember, star is always the line voltage and the phase voltage are not the same in star. So you enter this, which is 415 over root of 3, right? And that gives 239.6, 239.6 volts. So at this point, because I'm going to do this division, remember this is a magnitude. This, my ZY here, has been given in the linear form. You need to represent it in the magnitude and direction. Okay. So you convert this as a complex number. What do you get? You get the magnitude to be what? 15 squared plus 10 squared. And what are you getting? So 15 squared plus 10 squared. You are going to get 18.03, right? So that gives 18.03. Um, then what's the angle? The angle is tan inverse of what? 10 over what? 50. Is that not it? And that is giving us what? So tan inverse of 10 out of 15. And that is equal to 33.69. Therefore, my ZY is simply equal to 18.03 angle 33.6. Whilst my voltage is simply equal to 236.69. 230 of sorry. So it was supposed to be 415 over root 3, right? The answer is 239.6. Sorry, I made a mistake. So it's 239 rather than 39. So I'll have my voltage equal to, so V is equal to 39.6 ampere over 18.033.6. What are you getting? So answer divided by 8, that is 13.3. Okay. So therefore, my current across the yellow fish, right, simply equal to punch this, get 13.3 of 13.3 angle. 0 minus this because you are dealing with the polar, you get negative 33.69 volts nicely. Take note of this. The second part of the problem is saying that we should find the magnitude and the current in the neutral conductor. So please, this formula is In in the neutral conductor is equal to IR plus IB plus IY. Now we have our IY, so it's simple. We have to find IR and I, similarly to what you were doing. So please convert. We are interested in the magnitude. Forget about the direction. So in my ZR, what do I get? I get square root of what? 10 squared plus 5 squared. So let's do this an informal way. 10 squared plus 5 squared. That gives me 5 root 5, right? So 5